Hello everyone, welcome back, and in today's video we are going to solve a few problems from the mechanics section. So in this first problem we have four identical rods, each of mass m and length 2d. They are joined to form a square. The square is then spun around its center as shown in the figure at an angular velocity of omega. What is the magnitude of the force that the joints between the rods? So they're talking about these four joints over here. We have to find the force on these joints. Okay guys, so let's say this is one of those particular rods, and let's say this point O is the center of the square. So each point of this rod is being rotated in a circle of different radiuses, right? Okay, so now what is the force that is acting on this rod as a result of its rotation? So this distance over here is basically half the side of the square, so this is going to be d, right? So let's say if I take a dm mass over here, something like this, and let's say if I join it to a point O, a centrifugal force of dm omega square r will act on this mass dm, where r is its radius of rotation. Now by symmetry we can see that as we vary the element throughout the rod, the horizontal component of the centrifugal force is going to get cancelled out. So we only care about the vertical components, right? So let's say the force applied on the rod by the joints is F. Okay, so it'll be by symmetry F on both sides. So we can say 2F is simply the integral of dm omega square r. So let's call this angle as theta. So even this angle is going to be theta. So this is going to be dm omega square r cos theta. So now if I take omega square common, it will be dm. The inner integral will be integral of r cos theta times. Now let's say I define x-axis and y-axis in these particular directions. Integral of r cos theta dm, if I divide this term by the total mass and multiply it with the total mass, this term over here is simply the y-coordinate of the center of mass, right? Which basically is going to be d, right? This is going to be m omega square times d. So basically it is as good as saying that we can keep a mass of capital M at the center of mass and write the centrifugal force on that particular mass instead. It will be exactly the same as net centrifugal force acting on this entire rod. So from here F comes out to be m omega square d by 2. Okay guys, so but the thing is there is a catch in this problem. This is not the answer to the given problems. If you observe one of these joints, it is actually supporting two of these rods, right? So let's say the joint that was attached to this end of the rod, if I draw it over here, the rod will apply a force of F in this particular direction, but it is trying to make sure that even this rod doesn't fly apart, right? So that rod will apply a force of F on the joint as well. So hence the net force on the joint will be root 2 times of F. So and the final answer is going to be m omega square d by root 2. Okay, so that was it for this problem. So now let's move on to the next problem. Okay guys, so in this question we have two rings, and ring 1 is actually fixed and ring 2 rotates about the point O. So it is basically performing fixed axis rotation about the vertical axis passing through the point O. So the question is to find the maximum speed of the other intersection point of the two rings. Okay guys, so let's say this is how the situation is looking like, and let's call the intersection point with some name, let's say I. Let's call the center of this circle as O dash. Okay, so in this question we have to analyze the speed of the intersection point. So as the ring number 2 is performing fixed axis rotation, we can say that each point on this ring is performing circular motion about the point O. So if you want to write the velocity of any particular point, let's say this particular point, it will be r times omega, and the direction is perpendicular to the position vector, right? Simple. Let's analyze what is happening with the intersection point. So if I duplicate this ring and place it over here, so this is how the situation is looking after some time t0, let's say. So the intersection point is now over here. Now if I again duplicate this and if I place it here, we can see that the intersection point is over here now. So as we can see from our diagram that the intersection point is continuously moving along the circumference of ring number 1. In other words, we can say that the instantaneous displacement of the intersection point is along the tangent to ring number 1. So that was the whole concept. So now let's say I join point O and O dash. So this is a fixed vector, right? O dash. So this distance is capital R. Now let's say I join these 2 points. Even this length is capital R vector. And now let's say I join O to I, and let's call this vector as r vector. So r vector is essentially the position vector of our intersection point, right? Okay guys, so now the thing is we know the net speed of the point I, right? As it is performing circular motion about the point O, the net speed is going to be r omega, and it is going to be perpendicular to our position vector, right? Now let's say I drop a perpendicular onto our position vector, and let's call these two angles as theta. So even this angle is going to be theta, and now the component of the speed along the tangent to the ring 1, which is the velocity of the intersection point, right, is simply r omega sine theta. So that's the answer. So velocity of intersection point, let's call it v int, r omega sine theta. Now r is basically the modulus of this vector, and that we can determine from geometry. we can see that it is r sine theta plus r sine theta, which is 2r sine theta. So if I put it over here, it'll be 2r omega sine square theta. So now we are required to find the max value of this expression, and that happens when sine theta equals 1. So the maximum value comes out to be 2r omega, which is going to be 6 meters per second. Okay, and this happens when theta is 90 degrees. So now let's move on to the next problem. Okay guys, so in this problem we have a thin circular wooden hoop whose mass is capital M and radius is capital R. It rests on a horizontal frictionless plane. A bullet of mass m that is moving with a velocity of v strikes the hoop and it becomes embedded in it as shown in the figure. Find the ratio velocity of the cm divided by omega of the center of mass velocity vcm and the angular velocity omega of the hoop and bullet system after collision. So, and the mass of the hoop is 3 times the mass of the bullet. Okay guys, so this is how the situation is looking like before collision. And after collision, the mass m gets embedded onto this ring. The center of mass, which is going to be over here, will have some velocity now. Now after getting embedded, they'll perform a combined translation and rotational motion. Let's just say its center of mass of this system is over here. It will gain some velocity. Let's call it vcm. And the rigid body is going to gain some omega in the counterclockwise sense. Let's call it omega. Well, now the question is pretty simple. We have two variables, omega and vcm, right? So we need two equations, and for those two equations we can use momentum and angular momentum conservation. Now why is the momentum conserved again? Because the net force will be 0, right? Because while these two masses are colliding, the bigger mass will apply a force F on the smaller mass, and the smaller mass will apply a force of F on the bigger mass, and this is by Newton's third law. And hence if we take both of them as a system, we can conserve momentum, right? Initially the velocity of the smaller mass was v, so the initial momentum is mv. And finally the combined center of mass is moving with a velocity of vcm. The final momentum is 4m, which is the total mass, times vcm. And from here we can get vcm equals v by 4. And for the second equation we can use angular momentum conservation. For conserving angular momentum, I guess the best choice would be the center of mass of the new system. So let's call that point as c. So we can conserve L about c. So the angular momentum about the point c, okay, for that we have to determine the distances, right? So as the masses are in the ratio of 3:1, the distances have to be in the alternate ratio, that is of 1:3. 1/4 of r, which is r by 4, and this distance is 3r by 4. Now initially what is happening is only this mass m has a velocity v, right? So the angular momentum of a particle, we can write it as m v times the perpendicular distance, which is 3r by 4, right? I'm not taking directions into consideration because all of the components are in the same direction, right? Which in this case is out of the plane. Now angular momentum about c, in the final case, now as you're balancing the angular momentum about the combined center of mass, the angular momentum simply ICM times omega. But let's say you chose some other point. Let's, for example, the point that lies on the line of action of this mass m. Initial angular momentum would be 0, but while writing the final angular momentum, there will be an ICM omega, but plus you have to do m RCM cross VCM of the system's center of mass. Okay, so in this case, it's quite straightforward. Now I of the system about the center of mass. So due to the ring is going to be 3m r squared plus the mass of the ring d squared, and d is r by 4 here. And this is by parallel axis theorem. And then we also have to add the contribution due to the smaller mass, which is going to be m times 3r by 4 whole squared. So this will be 15 by 4 mr squared after calculation. Okay, so now after equating these two terms, we'll get the omega as v divided by 5r. Now in the question, they ask the value of VCM by omega, and that will come out to be 5r divided by 4. So now let's move on to the last problem of the day. So the question might not be visible to you guys. I'll just read it out. So in this question, we have a train which has a mass of capital M, and it is traveling on a frictionless straight horizontal track with a constant speed of v. Snow starts to fall vertically and sticks to the train at a rate of rho, where rho has units of kilograms per second. The train's engine keeps the train moving at a constant speed v as snow accumulates on the train. Okay, so now the question that we have to solve is we have to find the minimum power required from the engine to keep the train traveling at a constant speed of v. Okay guys, so this is how the situation is looking like. So the falling snow increases the mass of our bright train at a rate of rho kg per second. Hence, as a result, the velocity, if there was no external force, the velocity of the cart will definitely come down, right? So we have to give it some external force F if we want to make sure to run it at constant speed. And this force F, we can easily write it as the rate of change of momentum of our train. So, and the momentum of the train is simply going to be the mass times its velocity. velocity, and the velocity, as it is given to be a constant, it does not vary with time, so we can take it out of the derivative. So this would simply be v dm by dt, and dm by dt is basically the rate of change of mass of our train. Snow is responsible for increasing the mass, and dm by dt of the snow is given to be rho. So now we have the force that we need to apply in order to make sure that the train moves at a constant speed. The power that we have to provide is going to be F dot V, rho V multiplied by V, which is rho V squared. Okay guys, so now the reason I took this problem is to emphasize on one thing. Let's try to find the same answer with the help of energy conservation. So by using differential form of work energy theorem, we can say that so if I basically say the small work that the external agent has to do equals a small change in kinetic energy of our train, okay, and if I divide both sides by dt, just so to obtain the rate of doing work, so this will translate into the power that we have to deliver, and this would simply be equal to the time rate of change of our kinetic energy. So this would be ddt of half mv squared, and that is simply going to be half rho v squared. So if you observe something, we are getting exactly half of the answer that we got over here. Now the reason for that is in the energy conservation equation, we are not accounting for the dq, or basically the energy that we lost in the form of heat, and that's the reason that we are getting the value of the power required to be less. So if you divide this with dt as well, we'll get the rate of heat loss. So comparing this equation and this equation, the rate of heat loss will also be exactly the same as dk by dt. If you excluded the rate of heat loss, then you'll get the wrong answer. Now why is heat being lost here? Okay, so let's just consider one snow particle over here. If we observe things from the reference frame of the cart, then we have to give this velocity v to our snow particle, right? And finally what will happen is that when the snow particle hits the bottom surface, kinetic friction will start acting on the snow particle, and it will keep acting till it kills the velocity. So in this frame of reference, as you can see, some half dmv squared of the snow particle got completely destroyed by kinetic friction. Now where did this energy go? And the answer to that is it went in the form of heat, got dissipated into the atmosphere as heat. Now guys, heat lost, or basically the work done by kinetic friction, is a frame independent quantity, and therefore we can say that even in the ground frame, the heat lost is going to be exactly the same. Okay, so that was it for this problem guys, and hence that's the answer to this problem. So the answer will be rho v squared. So yeah, that was it for this video guys. If you have any doubts, you can comment down below, and that's it. Thanks for watching.